January 7th, 1945, Kummersdorf Proving Grounds, 40 kilometers south of Berlin. Obsolete Friedrich Halder watched through reinforced glass as technicians positioned the American shell on the test stand. 3 weeks earlier, this 5-inch artillery round had failed to detonate during the Ardennes offensive, embedding itself in frozen Belgian soil, where Wehrmacht recovery teams retrieved it before American forces could secure the area. Now, in the cold fluorescent light of Germany's primary ballistics laboratory, Halder was about to witness something that would fundamentally alter his understanding of what the Reich was facing. Preparing and narrating this type of story took us long efforts and hard work, so if you are enjoying the story, please consider subscribing to our channel. The shell's nose contained a device no larger than a wine bottle, packed with miniature vacuum tubes and circuitry that had somehow survived being fired at forces exceeding 20,000 times Earth's gravity. German engineers had spent years concluding such technology was physically impossible. The Americans had not only built it, but were manufacturing these devices by the hundreds of thousands, equipping every artillery shell with electronics more sophisticated than anything in Germany's most advanced research laboratories. Within hours, Halder would write a classified report stating that Germany's vaunted 88mm Flak system, the weapon that had defined German anti-aircraft doctrine since Spain, had been rendered strategically obsolete by an enemy whose industrial capacity exceeded German comprehension. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The story of how German engineers came to examine American proximity fuses, and what that examination revealed about Allied technological superiority, began not at Kummersdorf, but in the forests of Belgium during the desperate winter offensive of 1944. When German forces launched Operation Wacht am Rhein on December 16, 1944, commanders anticipated facing conventional American artillery. What they encountered instead was something that defied every assumption about what artillery could achieve. Obergefreiter Klaus Weber, a veteran of 3 years on the Eastern Front, had survived Kursk, had endured countless Soviet barrages, and considered himself experienced in the lethal calculus of artillery warfare. On the morning of December 21, 1944, south of Malmedy, Belgium, he learned that his experience meant nothing against what the Americans had deployed. The shells were detonating in mid-air, 20 to 30 feet above the snow-covered ground, showering down shrapnel that turned foxholes from sanctuary into death trap. Weber pressed himself into frozen dirt, watching men around him torn apart by steel fragments that seemed to rain from every direction simultaneously. Traditional artillery exploded on impact, creating craters and sending shrapnel horizontally. Soldiers in foxholes remained relatively protected, the fragments passing overhead while the crater absorbed much of the blast. But these American shells exploded perfectly above German positions with surgical precision, regardless of terrain or visibility. Each airbursting shell covered an area 10 times larger than a ground burst, the fragments spreading in a cone-shaped pattern that penetrated even log-reinforced bunkers. For the first time in his combat experience, Weber felt genuinely helpless. There was no defense, no tactical adaptation, no amount of training or courage that could protect against weapons that exploded precisely where they would inflict maximum casualties. When Weber's unit finally retreated on December 23rd, carrying their dead and wounded through the frozen forests, they left behind more than just casualties. Several unexploded American shells lay in the snow, their nose fuses intact. Wehrmacht recovery teams, operating under strict orders from higher headquarters, worked methodically to secure these shells before American forces could retrieve them. The shells were carefully packed in straw-filled crates, loaded onto trucks, and transported under armed guard to Berlin. Someone in the German High Command understood that these weapons represented more than just tactical superiority. They represented a technological revelation that demanded immediate analysis. The shells arrived at Kummersdorf on December 28, 1944. The proving grounds, established in 1871, had served as Germany's primary weapons testing facility for 7 decades. Here, German engineers had developed the 88mm Flak gun, tested the Tiger tank's armor, and refined countless weapons that had made the Wehrmacht feared across Europe. The facility's reputation for engineering excellence made it the obvious choice for examining captured Allied technology. But the men who gathered in Laboratory 7 on the morning of January 2, 1945, were about to confront a humbling truth. German engineering excellence, legendary though it was, had been surpassed by an enemy they had underestimated. Obsolete Friedrich Halder, assigned to the Heereswaffenamt's Artillery Development Section, had earned his doctorate in electrical engineering from the Technical University of Berlin in 1936. His dissertation on radio frequency oscillators had been considered groundbreaking at the time. He had spent 8 years working on German proximity fuse programs that had been repeatedly cancelled due to insurmountable technical obstacles. Now, examining the American fuse under a magnifying glass, Halder experienced something close to professional despair. The Americans had solved every problem that had defeated German engineering. The device measured approximately 8 inches long and weighed just over 2 pounds. Inside its steel casing, visible through the transparent potting compound, lay approximately 130 miniaturized electronic components. 4 vacuum tubes, each smaller than Halder's thumb, were mounted in shock-absorbing wax. A battery assembly used centrifugal activation, spinning electrolyte into contact with plates when the shell was fired. Safety circuits prevented premature detonation. A complete radio transmitter and receiver, operating at frequencies around 200 MHz, occupied space smaller than a cigarette pack. The engineering was elegant, sophisticated, and utterly beyond what German industry could replicate given current resource constraints. Halder spent January 2nd through January 5th carefully disassembling the fuse, photographing each component, measuring voltages and frequencies, documenting every aspect of its operation. His team included Dr. Wilhelm Runge, who had examined the British H-2S magnetron captured at Rotterdam in February 1943, and several engineers from Telefunken and Siemens. Together, they represented perhaps the finest collection of electronics expertise available to Germany in January 1945. Their collective conclusion, delivered in a classified report dated January 7, 1945, was devastating in its honesty. The report, later recovered by American forces and now housed in the National Archives, stated without equivocation that the American proximity fuse represented a technological achievement Germany could not match with available resources. The miniaturization techniques required manufacturing capabilities Germany no longer possessed after years of strategic bombing. The vacuum tubes had to survive acceleration forces that would destroy conventional tubes, requiring glass composition and annealing methods German industry had not mastered. The radio circuitry operated at frequencies German equipment could barely detect, much less generate with comparable power and reliability. Most critically, the fuse was clearly a mass-produced weapon, not a laboratory prototype. The quality of manufacture, the standardized components, the sophisticated but practical design all indicated industrial production measured in hundreds of thousands of units. This last observation carried profound implications. German engineers could potentially reverse engineer a few working prototypes given enough time and resources. But the Americans were producing these devices faster than German factories could produce conventional artillery shells. The industrial capacity required to manufacture proximity fuses at such scale exceeded Germany's entire electronics production capacity. This was not merely technological superiority. This was industrial dominance of an order that made German resistance strategically futile. On January 7, 1945, Halder conducted the live firing test that would provide final confirmation of the fuse's capabilities. A standard German 88mm Flak gun had been positioned on the test range, fitted with instruments to measure barrel pressure, acceleration forces, and projectile spin rates. The American fuse was carefully installed in a German shell, modified slightly to accommodate the different threading. If the fuse could survive being fired from a German gun and still function properly, it would prove the device was not specifically calibrated for American artillery, but represented a universal technology applicable to any gun system. The test was scheduled for 1,000 hours. Halder, Runger, and approximately 20 observers gathered in the reinforced observation bunker 200 meters from the gun. A radio-controlled target drone, one of the few still operational given Germany's desperate fuel situation, circled at an altitude of 1,000 meters, approximately 3,000 feet. The flak gun was aimed not at the drone, but at a point 500 meters in front of it, calculated to place the shell on an intercept course. In conventional anti-aircraft gunnery, this shot would require extraordinary luck to achieve even a near miss. With the proximity fuse, it should be devastatingly effective. The gun fired at precisely 1,000 hours and 3 seconds. Through binoculars, Halder watched the shell arc toward the drone. At a distance of approximately 75 meters from the target, the shell exploded in a brilliant flash, sending fragments in all directions. The drone, struck by multiple pieces of shrapnel, tumbled from the sky trailing smoke. The entire engagement, from firing to destruction, had taken less than 4 seconds. A conventional timed fuse, even if perfectly set, would have exploded either too early or too late, given the variables of air density, temperature, and projectile velocity. The proximity fuse had automatically compensated for all these factors, detonating at the optimal moment for maximum effect. Halder lowered his binoculars and turned to face the assembled observers. "Gentlemen," he said quietly, "what we have witnessed represents the future of anti-aircraft warfare. Unfortunately, it is a future that belongs entirely to our enemies. The 88mm Flak system, which has served as the backbone of our air defense since 1936, has been rendered obsolete by a weapon we cannot produce in operationally significant numbers before the war's end. We are defending the Reich with technology from the previous decade against enemies deploying weapons we believed impossible to build." The silence that followed this statement was profound. Several officers present had spent their entire careers working with 88mm Flak systems. They had refined tactics, trained crews, coordinated thousands of batteries across Germany and occupied territories. They had shot down thousands of Allied aircraft, inflicted grievous losses on bomber formations, forced changes in Allied tactics and strategy. Now they were being told that their weapon system, their doctrine, their expertise had been surpassed by American technology so advanced that German industry could not hope to replicate it. The 88mm Flak gun, officially designated Flak 18, 36, or 37, depending on the model, had been one of Germany's most successful weapons. Developed in the early 1930s by Krupp, building on experience from the First World War, the 88 combined long range, high muzzle velocity, and excellent accuracy. The gun could fire a 9.4 kilogram shell to altitudes exceeding 10,000 meters, approximately 33,000 feet. Rate of fire was 15 to 20 rounds per minute with a well-trained crew. The weapon had proven so effective that it had been adapted for anti-tank use, becoming perhaps the most feared anti-armor weapon of the war. By 1945, Germany had deployed approximately 10,000 88mm Flak guns across all theaters, with the majority concentrated in the defense of the Reich against Allied strategic bombing. These guns were organized into batteries of 4 to 6 weapons, coordinated by radar directors and fire control computers. The system represented a sophisticated integration of technology, tactics, and training. Crews underwent months of specialized instruction, learning to calculate lead angles, set fuse timings, coordinate with radar operators, and maintain the complex gun mechanisms. The investment in training alone represented years of cumulative experience. Yet, despite this sophistication, the 88mm system had fundamental limitations that proximity fuses would exploit mercilessly. Conventional anti-aircraft fire required either a direct hit, which was extraordinarily difficult against fast-moving targets at high altitude, or a near miss with a properly timed fuse. The timing calculation depended on accurately estimating target altitude, speed, and course. Even with radar assistance and mechanical fire control computers, these calculations contained inherent errors. A shell might explode 100 meters behind a bomber, or 200 meters ahead, or at the wrong altitude entirely. The bomber would fly through the engagement unscathed while the gunners adjusted their calculations for the next salvo. Statistics from 1944 demonstrated the inefficiency of conventional flak. German records, meticulously maintained even as the Reich collapsed, showed that approximately 10,000 rounds of 88mm ammunition were required to down a single Allied heavy bomber. Some estimates ranged as high as 16,000 rounds per kill. This represented an enormous expenditure of ammunition, barrel wear, crew time, and industrial resources for relatively modest results. The 8th Air Force alone lost approximately 6,000 bombers over Europe during the entire war, a grievous toll for the crews involved, but sustainable given American industrial production of approximately 18,000 B-17 seconds and B-24 seconds. The mathematics were brutally simple. If Germany fired 10 million rounds of 88mm ammunition during 1944, achieving perhaps 1,000 bomber kills, the exchange rate was economically unsustainable. Each 88mm shell cost approximately 20 Reichsmarks to produce, requiring precision machining, high-quality steel, and explosive compounds. 10,000 shells represented 200,000 Reichsmarks, equivalent to the cost of several fighter aircraft. Meanwhile, American factories were producing bombers faster than German flak could destroy them, and training replacement crews faster than casualties could deplete the force. Proximity fuses fundamentally altered this calculus. If every shell became an effective airburst, detonating at optimal range without requiring precise timing calculations, the kill probability would increase by factors of 5 to 10. Instead of 10,000 rounds per bomber, perhaps 1,000 rounds would suffice. Perhaps even fewer if multiple shells exploded near a target simultaneously. The operational implications cascaded through every aspect of air defense doctrine. Dr. Wilhelm Runge, who had witnessed the test from the observation bunker, understood these implications with painful clarity. Runge had been present at the examination of the British cavity magnetron in February 1943, the device that had explained why German U-boats were being slaughtered in the Atlantic. Now, less than 2 years later, he was witnessing another technological revelation that exposed German inferiority in a critical domain. The pattern was unmistakable. Allied scientists were consistently solving problems that German experts had declared impossible, then deploying the solutions at industrial scale that German factories could not match. That evening, January 7, 1945, Runge drafted a memorandum to Reichsminister Albert Speer, the armaments minister who controlled what remained of German war production. The memorandum, preserved in captured German documents, was remarkable for its stark honesty at a time when defeatism could result in execution. Runge wrote that American proximity fuses represented a war-winning technology against which Germany had no effective counter and no realistic prospect of developing one before the war's conclusion. He estimated that if Allied bombers were equipped with proximity-fused bombs for anti-flak suppression, German air defense casualties would increase by 300%, while effectiveness decreased proportionally. More troubling, Runge noted that the proximity fuse was merely one example of Allied technological superiority across multiple domains. The cavity, magnetron, the proximity fuse, the atomic bomb program about which German intelligence had gathered fragmentary reports, all demonstrated that Allied science had surpassed German research in critical areas. This superiority stemmed not from any inherent German intellectual deficiency, but from material and industrial advantages that Germany could not overcome. Allied scientists worked in laboratories that were never bombed, with unlimited resources, supported by industries producing war material in quantities that dwarfed German capacity. German scientists worked in bombed-out facilities, with chronic material shortages, supporting an industrial base that was being systematically destroyed from the air. Speer received Runge's memorandum on January 10, 1945. By that point, the Ardennes offensive had collapsed completely, with German forces retreating across the Rhine having suffered approximately 100,000 casualties, including nearly 800 tanks and assault guns destroyed or abandoned. The strategic situation was desperate. Soviet forces were advancing through Poland toward East Prussia, Allied armies were preparing to cross the Rhine. German cities were burning under relentless bombing. The war was clearly lost to anyone willing to see reality clearly. Yet Speer ordered a response nonetheless. If German industry could not produce proximity fuses in war-winning quantities, perhaps Germany could develop countermeasures that would reduce their effectiveness. Perhaps German scientists could design electronic jamming systems or develop tactics that would minimize exposure to proximity-fused artillery and anti-aircraft fire. The Reichsminister's directive, issued January 14, 1945, ordered maximum priority investigation into proximity fuse countermeasures, with initial recommendations due within 2 weeks. The scientists and engineers who received this directive understood its futility. Electromagnetic jamming required knowing the operating frequency and modulation characteristics of the fuses. Without multiple intact examples to study, determining these parameters precisely enough for effective jamming was impossible. Even if jamming systems could be developed, deploying them across thousands of flak batteries and field artillery positions would require manufacturing capacity that no longer existed. The bombed factories, the disrupted supply chains, the lack of rare materials, all made large-scale electronic warfare deployments impossible in early 1945. Tactical countermeasures were equally problematic. Aircraft could not avoid proximity-fused flak by changing altitude or course, as the fuses would detonate regardless. Flying lower increased vulnerability to lighter anti-aircraft weapons and small arms fire. Flying higher reduced bombing accuracy. Dispersing formations reduced the number of aircraft hit by each shell, but also reduced the concentration of defensive fire against Allied fighters, making bombers more vulnerable to interception. Every tactical adaptation created new vulnerabilities while providing minimal protection against the fundamental advantage proximity fuses provided. The examination of additional captured proximity fuses during January and February 1945 revealed the full scope of American production sophistication. Each fuse examined showed consistent quality, indicating robust manufacturing processes with effective quality control. Component markings identified multiple manufacturers, suggesting a distributed production network that would be essentially impossible to disrupt through strategic bombing. Some fuses bore date codes showing manufacture in mid-1944, indicating the technology had been in mass production for at least 6 months before German forces encountered it in the Ardennes. This timeline explained several mysteries that had troubled German commanders during the latter half of 1944. Allied anti-aircraft fire during the Normandy campaign had been unexpectedly effective, downing German aircraft with a consistency that seemed beyond normal improvement in crew training or radar coordination. Intelligence reports from the Eastern Front, where the Soviet Union had received substantial American military aid, mentioned artillery that exploded in the air with unusual precision. Reports from Italy described similar experiences. The proximity fuse had been deployed globally, equipping Allied forces across all theaters with technology that provided tactical advantages German forces could not counter. Generaloberst Alfred Jodl, chief of the Wehrmacht operations staff and one of Hitler's closest military advisors, was briefed on the proximity fuse findings on January 20, 1945. Jodl, a professional officer with decades of experience, grasped the strategic implications immediately. If American artillery could inflict casualties at rates 5 to 10 times higher than conventional shells, German defensive operations would become unsustainable. Field fortifications would provide no protection against airbursting shells. Counterattacks would be devastated by artillery barrages that could interdict entire areas with lethal efficiency. German tactical doctrine, refined through years of warfare, had to be completely rewritten to account for weapons that made traditional defensive positions death traps. Jodl ordered the Wehrmacht operations staff to develop new defensive doctrines, assuming universal Allied deployment of proximity fuses by spring 1945. The staff officers assigned to this task produced several working papers during late January and early February, documents that revealed the impossible situation facing German forces. Traditional defense in depth, relying on successive trench lines and fortified positions, would not work against proximity-fused artillery that could sweep entire defensive zones. Mobile defense, using counterattacks to disrupt enemy advances, would expose German forces to artillery barrages against which movement in the open was suicidal. Static defense in fortified positions would be equally futile, as airbursting shells would suppress any position that revealed itself by firing. The staff officer's conclusion, never formally submitted because events overtook their analysis, was that defense against an enemy equipped with proximity fuses required either air superiority, which Germany no longer possessed, or artillery superiority, which was impossible given Allied production advantages. In the absence of either, German forces could only delay Allied advances through calculated retreats and limited counterattacks, accepting that casualties would be disproportionately high and ultimate defeat inevitable. This was not defeatism. This was mathematical reality based on technological disparity. While German engineers studied captured American proximity fuses, American forces were deploying them in ever-increasing numbers across the European theatre. Following the authorization for unlimited use on December 21, 1944, production was ramped up to meet explosive demand from field commanders who recognized the weapon's devastating effectiveness. By February 1945, American artillery battalions in Europe were receiving proximity-fused ammunition as standard issue, with conventional shells increasingly reserved for specific missions where airbursts provided no advantage. The psychological impact on German troops was profound and well documented in interrogation reports from prisoners captured during early 1945. Unlike the U-boat crews who had faced cavity magnetron-equipped radar, German soldiers facing proximity-fused artillery could see and understand what was killing them. They watched American shells explode overhead with perfect consistency. They witnessed the devastation as fragments rained down on positions that would have been safe from conventional artillery. They experienced the helplessness of facing a weapon against which there was no defense except staying constantly under cover, which made conducting military operations impossible. Obergefreiter Klaus Weber, who had survived the initial encounters with proximity fuses in December 1944, was captured by American forces near Remagen on March 10, 1945. During interrogation, he described the weapon's psychological effect in terms that Allied intelligence found remarkably articulate. Weber explained that conventional artillery was terrifying but comprehensible. Soldiers learned to gauge the sound of incoming shells, estimate impact points, and take cover in foxholes or behind terrain features. Survival depended partly on luck, but also on experience and quick reactions. Proximity-fused artillery removed the element of skill entirely. The shells exploded without warning, often before soldiers could hear them approaching due to their high velocity. The fragments came from above, targeting the head and shoulders where body armor provided minimal protection. Foxholes became killing zones rather than refuges. Weber described watching his entire squad killed by a single proximity-fused shell that exploded directly overhead while they sheltered in what should have been a safe position. He had survived only because he had been slightly separated from the group, detailed to carry ammunition forward. When he returned minutes later, his comrades were dead, killed by a technology he could neither understand nor counter. The interrogation report noted that Weber displayed symptoms consistent with combat stress reaction, including emotional flatness, difficulty concentrating, and recurring statements about the futility of resistance. The interrogating officer, a captain with psychological training, observed that Weber's demoralization stemmed not from fear of death itself, which soldiers had learned to accept, but from the specific helplessness of facing proximity fuses. The weapon stripped away any sense of control or agency. Soldiers could not protect themselves through skill or courage. They could only hope the shells fell elsewhere, which was not a basis for maintaining combat effectiveness. Similar reports from hundreds of prisoners captured during early 1945 painted a consistent picture. German soldiers were increasingly unwilling to remain in positions subject to American artillery fire. Units were experiencing discipline problems, with soldiers refusing orders to occupy forward positions or conduct operations in areas where proximity-fused fire was likely. Some units were functionally combat ineffective despite having adequate manpower and equipment, simply because soldiers would not expose themselves to weapons they could not survive through any amount of training or tactical skill. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. German artillery officers, examining the tactical situation during February and March 1945, recognized that proximity fuses represented an evolution in warfare comparable to the introduction of breech-loading artillery in the 19th century, or indirect fire in the early 20th. Each of these innovations had rendered previous doctrines obsolete, forcing complete reorganization of tactics and training. But those transitions had occurred during peacetime or early in conflicts, allowing armies to adapt gradually. The proximity fuse had appeared in the final months of a losing war, when Germany lacked the time, resources, and industrial capacity to respond effectively. Major Heinrich Brandt, serving as artillery officer for the 7th Army defending the Saar region, wrote in his February 1945 diary entry that American artillery had become the decisive weapon on the Western Front. Brandt noted that German artillery, firing conventional shells, could achieve temporary fire superiority by concentrating batteries against specific targets. But American counter-battery fire, using proximity fuses, would invariably locate and suppress German positions within minutes. The cycle repeated endlessly. German guns would fire, American counter-battery radar would locate them, proximity-fused shells would airburst over German positions, and German crews would take casualties, while American guns remained relatively safe behind their technological advantage. Brandt's diary, recovered after his capture in March 1945, contained detailed calculations showing the disparity. A German battery firing 100 shells might suppress an American position temporarily. The American response, using perhaps 20 proximity-fused shells, would inflict casualties that rendered the German battery combat ineffective. The exchange rate was unsustainable. German artillery was losing the counter-battery duel through technological inferiority rather than tactical incompetence or insufficient numbers. The situation was even worse for German anti-aircraft defenses. During March 1945, American and British bombers began using proximity-fused bombs specifically designed for flak suppression. These bombs, dropped from high altitude over known flak concentrations, would airburst at predetermined altitudes, showering German gun positions with fragments. Traditional bombing of flak sites had been relatively ineffective because gun positions were small, well camouflaged, and protected by earthworks. Even near misses rarely disabled guns or killed crews. Proximity-fused bombs changed this calculus completely. A single bomb, airburst over a flak battery, could disable multiple guns simultaneously by wounding or killing exposed crew members. Gun shields provided no protection against fragments raining from above. Earthworks and sandbag revetments were useless. Flak batteries had to either disperse to distances that made coordinated fire control difficult or accept casualty rates that would deplete trained crews within weeks. Neither option was sustainable. General Major Wolfgang Pickert, commander of 3 Flak Corps defending the Ruhr industrial region, reported in early March 1945 that his batteries were experiencing crew casualties at 3 times the rate from earlier in the war, despite fewer Allied bombers reaching his defensive zone. The bombers were now conducting flak suppression runs before main formations arrived, dropping proximity-fused bombs that forced his crews to take cover rather than engage targets. By the time main formations passed overhead, German guns were suppressed, allowing bombers to attack with minimal interference. The tactical revolution was complete. Allied technology had neutralized Germany's carefully constructed air defense network. The final reports from Kummersdorf, dated March 8, 1945, represented the culmination of 2 months of intensive study of captured American proximity fuses. The research team, now expanded to include representatives from every major German electronics firm still operating, had examined dozens of fuses recovered from various theaters. Their findings, compiled in a comprehensive technical document running over 200 pages, provided a detailed autopsy of German technological defeat in the electronics domain. The report documented not just the proximity fuse's technical specifications, but the industrial ecosystem required to produce such devices at scale. American factories were manufacturing approximately 70,000 fuses daily by early 1945, representing over 2 billion individual electronic components annually. Each fuse required precision machining, specialized glass for vacuum tubes, high-purity copper for electrical contacts, and sophisticated assembly procedures. The fact that American industry could produce these devices in such quantities while simultaneously building aircraft, tanks, ships, and conventional ammunition demonstrated industrial capacity that Germany simply could not match. More troubling were the cost projections. German engineers estimated that if the Reich attempted to replicate American proximity fuse production, each unit would cost approximately 150 to 200 Reichsmarks, given Germany's material constraints and damaged industrial infrastructure. The Americans, benefiting from economies of scale and undamaged factories, were producing fuses for approximately $18 each, roughly 45 Reichsmarks at wartime exchange rates. Germany would spend 4 times as much per unit while producing a fraction of the quantity. The mathematics made any catch-up program economically impossible. The Kummersdorf report concluded with a section that departed from pure technical analysis to address broader strategic questions. The authors noted that proximity fuses represented merely one example of Allied technological superiority across multiple domains. British cavity magnetrons had revolutionized radar. American industrial techniques had enabled production rates that dwarfed German capacity. Soviet T-34 tanks had proven superior to German armor in critical respects, despite Germany's vaunted engineering excellence. The cumulative effect was that Germany was fighting a war of the 1940s with increasingly obsolete weapons, while enemies deployed technologies that represented the next generation of warfare. This observation was not defeatism, the report carefully stated, but recognition of reality necessary for planning whatever operations remained before the inevitable conclusion. German forces could not win battles through technological superiority, as they had often done earlier in the war. Victory, where achievable at all, would come only through tactical skill, operational excellence, and strategic positioning. These factors could delay defeat but could not reverse the fundamental technological and industrial imbalances that now dominated the war. Obsolete Friedrich Halder, who had overseen the proximity fuse examination from its inception in early January, was reassigned in mid-March 1945 to a combat engineering unit defending Berlin. The Kummersdorf facility was evacuated on March 21st as Soviet forces advanced toward the capital. Halder's final act before departing was to ensure that all documentation related to the proximity fuse study was properly archived and, more importantly, that copies were prepared for potential surrender to American forces. He understood that this research represented valuable intelligence that might prove useful in post-war negotiations. Halder survived the war, surrendering to American forces on May 4, 1945. During interrogation, he provided detailed testimony about German proximity fuse research and the examination of captured American devices. His interviewers, technical intelligence officers from the U.S. Army's Ordnance Department, were impressed by the thoroughness of the German analysis and the honesty with which German engineers had acknowledged their inability to replicate American achievements. The interrogation reports noted that Halder displayed no bitterness about German defeat, only professional respect for American engineering and recognition that industrial capacity had proven as decisive as any battlefield factor. The broader statistical record confirmed what Halder and his colleagues had concluded from examining proximity fuses. During the final 3 months of the war in Europe, from March through May 1945, American forces fired approximately 600,000 proximity-fused artillery shells on the Western Front. German casualties from artillery, always the largest category of combat losses, increased by an estimated 40 to 60% compared to earlier periods with equivalent artillery expenditure. Medical records from German field hospitals showed that fragment wounds, particularly to the head and upper body, comprised an unusually high proportion of casualties during this period, consistent with airburst weapons firing from above. German air defences collapsed almost completely during these final months. The Luftwaffe, already reduced to token strength by fuel shortages and aircraft losses, found its remaining operations nearly impossible due to Allied air superiority, enforced partly through proximity-fused anti-aircraft fire. German pilots who survived the war consistently cited Allied flak as among their most feared threats, describing how American ships and ground units seemed to create impenetrable barriers of air-bursting shells that made low-level attack runs suicidal and high-altitude operations only marginally less dangerous. The human cost extended beyond casualties to the psychological toll on German forces, who recognized they were fighting with obsolete weapons against technologically superior enemies. Post-war interviews with German veterans revealed that awareness of technological inferiority was profoundly demoralizing in ways that simple numerical inferiority was not. Soldiers could accept being outnumbered and still fight effectively, believing that skill and courage might compensate for disadvantages. But soldiers facing proximity fuses understood that no amount of skill could protect them, that their tactical training and hard-won experience meant nothing against weapons that operated on principles they could neither see nor counter. Dr. Wilhelm Runge, who had examined both the British cavity magnetron and American proximity fuses, emigrated to the United States in 1947 under Operation Paperclip, the program that recruited German scientists for American research projects. He worked at the Army Signal Corps laboratories in New Jersey, contributing to post-war radar and electronics development. In a 1953 interview, Runge reflected on his wartime experiences examining captured Allied technology. He stated that the proximity fuse had represented a watershed moment in his understanding of the war's trajectory. When he first examined the device in January 1945, he knew immediately that Germany had lost not just the current war, but any future conflict against enemies who possessed such overwhelming industrial and technological advantages. Runge noted that German engineering during the war had often been brilliant but impractical, producing weapons like the Tiger tank or Me-262 jet fighter that were technically impressive but impossible to manufacture in war-winning quantities. American engineering, by contrast, prioritized mass production and reliability over theoretical performance. The proximity fuse exemplified this philosophy. It was not the most sophisticated possible design, but it was sophisticated enough to be devastatingly effective while simple enough to be manufactured by the millions. This approach, combining adequate technology with overwhelming quantity, had proven decisive across every theatre of the war. The legacy of the proximity fuse extended far beyond World War II. The technology pioneered for artillery shells evolved into guidance systems for anti-aircraft missiles, ultimately leading to modern air defense systems that can engage targets with near certainty at ranges exceeding 100 kilometers. The manufacturing techniques developed for mass-producing miniaturized electronics became foundations for the post-war electronics industry that revolutionized global commerce and communications. The scientists and engineers who worked on proximity fuses, both American developers and German analysts like Halder and Runge, contributed to technologies that shaped the second half of the 20th century. For the German soldiers who faced proximity fuses during the final months of World War II, the weapon represented something more immediate and visceral than technological progress or industrial achievement. It represented helplessness, the inability to protect oneself through any amount of training or courage. Veterans interviewed decades after the war consistently described proximity-fused artillery with particular dread, often stating they feared it more than conventional shells, more than air attacks, more than even the massed Soviet artillery barrages on the Eastern Front that had been far heavier in sheer tonnage. The psychological impact of facing a weapon against which there was no defense had proven as significant as the physical casualties inflicted. The examination of captured American proximity fuses at Kummersdorf in January and February 1945 had provided German engineers with complete understanding of how the devices worked and why German forces were suffering such disproportionate casualties. But understanding provided no solution. Germany lacked the industrial capacity, the material resources, and critically, the time to respond effectively. The 88mm Flak system, backbone of German air defense for a decade, had been rendered strategically obsolete by a technology Germany could not counter. German artillery, once among the finest in the world, had become demonstrably inferior to American guns firing proximity-fused ammunition. This technological inferiority was not the sole cause of German defeat. Manpower losses, fuel shortages, strategic overextension, and catastrophic leadership decisions all contributed to the Reich's collapse. But proximity fuses represented the broader pattern that made defeat inevitable. Allied nations, particularly the United States, possessed industrial and technological capabilities that Germany could not match, regardless of tactical skill or operational excellence. The proximity fuse was simply the most visible and immediate example of advantages that extended across every aspect of modern warfare. On May 7, 1945, Germany surrendered unconditionally. The Kummersdorf proving grounds were occupied by Soviet forces, who captured whatever equipment and documentation the evacuating Germans had left behind. American technical intelligence teams, racing to secure German research facilities before Soviet forces could strip them, arrived too late to recover most of the proximity fuse documentation. However, they located Friedrich Halder and several other key researchers who had ensured copies of critical reports survived. The post-war technical intelligence assessment, compiled by the U.S. Army Ordnance Department in late 1945, concluded that German understanding of American proximity fuses had been remarkably accurate and that German engineers had correctly identified the industrial and material constraints that prevented any effective German response. The assessment noted with some surprise the lack of bitterness in German technical personnel, many of whom expressed professional admiration for American engineering achievements, even while acknowledging those achievements had contributed directly to German defeat. This professional respect, transcending national animosity, reflected a shared understanding among engineers and scientists that technology was neither good nor evil, but simply capability deployed toward human ends. The proximity fuse had been a weapon of war, responsible for tens of thousands of German casualties. It had also been a masterpiece of miniaturization and mass production, advancing human knowledge of electronics and manufacturing. German engineers could simultaneously acknowledge its role in their nation's defeat and appreciate the technical brilliance of its design and execution. The story of German engineers examining captured American proximity fuses, understanding their implications, and recognizing the impossibility of any effective response, encapsulates the broader narrative of technological and industrial disparity that shaped World War II's outcome. It demonstrates how material advantages, when combined with scientific innovation and production capacity, can render courage and tactical skill insufficient for military success. It reveals the psychological dimensions of technological inferiority, the demoralization that comes from facing weapons against which there is no defense. Most fundamentally, it illustrates how wars between industrial nations are won not just on battlefields but in laboratories and factories, where the foundations of military capability are built. Friedrich Halder survived to see the world transformed by technologies pioneered during the war he had fought and lost. He witnessed jet aircraft become commonplace, guided missiles replace conventional artillery for certain missions, and electronics miniaturization progress from his captured proximity fuse to integrated circuits containing millions of components. In a 1978 interview, shortly before his death, Halder reflected that examining the American proximity fuse in January 1945 had been simultaneously the most professionally fascinating and personally devastating experience of his career. He had witnessed engineering excellence that exceeded anything he had imagined possible, and simultaneously understood that this excellence guaranteed his nation's defeat and likely his own death. That he survived to discuss it decades later was, he noted with characteristic German precision, a statistical improbability for which he remained grateful. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.